Thank everybody for having me. It's been great being here, and I appreciate the invitation to come and present at the symposium. I do represent Meter Group. We're a company in Washington State, so in the northwest corner of the United States. And we've been, well, first I also want to mention that I'm here as a representative, but all of the science and research that's gone into the development of our products was done by Dr. Galen Campbell and Dr. Doug Kobos, who work with me, who are colleagues, and unfortunately neither of them were able to be here to present for you, but I wanted to acknowledge them. I wanted to make everybody aware that Decagon Devices, Meter Group was formerly Decagon Devices, and we recently partnered with a company called UMS from Munich, Germany. And the combination of the two companies has created the company Meter Group. So I want to make everybody aware of that. Part of that transition, the thermal products group that I'm a part of is still operating under the Decagon Devices name. And so if you were to go and research or search out any information, you may not find it under the Meter Group website or under that name at this time, but in the next few months it will be transitioning to the new name. Our thermal properties measurements at Decagon started in the early 2000s. We were approached by NASA to help them. They knew that we had some knowledge on thermal properties measurements in soil, and they came to us and asked us to work with the Jet Propulsion's laboratory in California to develop this sensor. And so the sensor here, it's called the TECP probe, and the sensor was mounted on this arm on the Phoenix Mars lander. So in 2008, this device, the Phoenix Mars lander landed, and its sole mission was to take properties of the Martian regolith. And so the sensor itself had these needles on it, and then you can also make out there is a humidity sensor. There's also a wind sensor built in. And so as the arm reached out to take samples with the scoop, before it scooped the samples of the regolith, it would insert the sensor and take thermal properties measurements, as well as electrical properties of the regolith. And that would infer the liquid water content, the ice content, and the pore size distribution of the regolith. And then the area that was tested would be scooped by the machine and collected. And we were happy that NASA reported that our sensor was the only part of the mission that worked perfectly 100% of the time. So we're very proud of that, and much of what I'm going to be showing you is based off of the research that went into this probe, and that's why I brought that up. So some interesting applications that we've dealt with in our thermal group. Some of our customers and researchers have come to us to be used in some of these applications. And we use a needle sensor, and I brought a couple devices with me, and tomorrow I'll be hosting a workshop so that you can see those better in person and how they work. But a relatively small sample is needed, but some of these applications like skin or corneas from the eyes, that's a very small sample, and users are able to take layers of those samples and stack them up to insert the needle. And so even though there are some restrictions to how the measurement can be made with our devices, there are some ways to overcome that, and I'll talk a little bit more about that as well. But these are some of the main applications that we've seen in the past. We're also starting to give more attention to textiles. I've been speaking a lot with people in the underground heat source pump arena, and obviously soils and things like that are major backgrounds, so we have a lot of information there as well. Here's an outline of, basic outline of the things I'm going to cover. First I'll cover the steady state conductivity method, which I'm sure you're familiar with, but we'll discuss that because it leads into the line heat source method and how the line heat source method is an improvement. Recently, and I brought one of our prototype devices, we've been making even more improvements on the line heat source method, and so I'll share some of the advancements that we're seeing there. And then I'll also share some results of a test we did on some phase change materials that were in a gel and liquid forms that are proprietary, so I don't have very much information on the materials themselves, but I can share the data, and we'll present that to you and how we set up the testing with our device. So, like I said, you're probably familiar with this, but in the process of steady-state thermal conductivity, you will apply a known amount of heat to one side of a sample. The temperature is monitored on either side of the sample, and once the temperature on the cold side of the sample reaches equilibrium with the hot side, you can calculate for conductivity once you also consider the thickness of the sample. One of the major disadvantages with this is that if you're doing a basic test setup, that you're going to lose heat out the edges of the sample, anywhere that the plates aren't located, and so you'll have basically it will prolong the test period, and you'll also get inaccurate results. And one of the ways that people overcome that is by the guarded hot plate method. And one of the ways that we kind of started altering or thinking about moving away from this typical steady state method was to create the same sort of test with a radial setup. So using a cylindrical shape, we'll apply heat at the middle of the sample through a needle source throughout the sample. You still have a plate or an outside barrier in the form of copper or aluminum tubing, and the equations are more or less the same, taking into account the radius of the sample. It's also a lot easier to guard by just capping on the ends of the cylinder to keep heat from escaping. So some of the good things about the steady state method for determining conductivity are that it's pretty simple calculations. It's a direct method, so you're applying heat and measuring the temperature, and after inserting the thickness of the sample, it's fairly simple. You can also use large samples, which is good for real-world applications. Large samples can also be a bad thing if you don't have large samples, or if your material is scarce. You're also going to see the heat divergence. It's typically a laboratory method only. It's typically a large device that is going to be a benchtop unit. It's very slow, usually hours at a time, if not days, depending on your material that's being tested. One of the big downfalls is thermally induced moisture redistribution. We'll talk a little bit more about that. And then it's also very expensive. Even homemade devices that I've encountered cost the labs and the people that made them above $10,000 to make themselves. And if you're going to buy one off the market, you're probably looking closer to $15,000 and more. So the consequences of the thermally induced heat flow, again, this is one of the major faults or flaws of this method. So if a sample is completely dry or completely saturated, this issue of thermal induced water flow is typically not an issue. However, when a sample is sort of dry, the long heat times will move moisture throughout the sample, and this will give false readings and result in bad data. So the steady state method doesn't work well with these damp samples for that reason, and so the line heat source kind of overcomes that because it uses lower temperatures and is in more direct, it has a better contact typically. So similar to the radial steady state setup that I pictured, the line source is placed into the sample, and heat is applied to the temperature, heat is applied and temperature change is measured over time. It's actually detecting the temperature dissipation rates. And again, there's no need for guards or plates in this case. The differences in equation come when the measured response is compared with the predicted response using Fourier law model. And so here are the equations. This is the model that we use to generate the data to compare the values. These are the solutions to the different equations from Fourier's model that describe the heating and cooling cycle done in through our probes. So here's an image of one of our sensors. We have a couple of different sizes that different groups require. And again, I brought some of those with me. We can see those tomorrow during the workshop. When we put heat into the needle and only look at the heat being applied, the slope is straight and directly proportional to the sample's recessivity. Typically, those are simplified, and we plot the temperature against the log of time. Recessivity is directly proportional to the slope of the line. So this is just an equation that explains why the response is linear in time, and this is basically because the longer or the bigger t gets, so the longer time that passes, the smaller a will become, and over time, as it gets smaller and smaller, it can eventually be ignored, and so at this point, only the first two terms of this equation need to be considered. This slide shows the real data of temperature applied against the log of time, producing the straight line. And you can plot for T for the heating, or plot log, which is T over T minus T0 for the cooling. And then the difference in the resistivity of the 153 degrees centimeters over watts and the 144 degrees centimeters over watts. Basically, you can take those two, average them out to get your usable number. So there are some disadvantages to the transient line heat source method, and that's why we're making improvements. Ideally, these situations would all exist to get in a perfect world. Unfortunately, we have a certain needle size that we're restricted to. Again, we have various sizes that we have, but the heaters and the thermistors inside them are limited to the technology available for the sizes available for those parts. And then there's certain factors that cannot be controlled by the tester. Error is lower in the smaller needle, while the larger the needle gets, the higher the error can be. So we do make our needles as small as we can in diameter to reduce that error. But again, the longer read times will reduce error. So some of the good things about it is you can use a large or a small sample. Typically, samples only need to be about 5 to 10 millimeters thick. It's a fast method. Measurements are taken in 10 minutes or less. Typically, measurements can be taken in 1 to 2 minutes. It's a portable device. It can be used in a lab, but it can also be done in the field if that's where it's needed. Again, as mentioned before, it's using a lower heat So you don't have an issue with any of the thermally induced water flow that occurs with the steady state method. And then one of the biggest disadvantages is that it is a destructive method using a needle probe has to be inserted into a sample. And so if the sample cannot be sandwiched or surrounded, or cannot surround the needle, then it will need to be inserted. But we are beginning work on a thin film surface sensor that would be able to be placed on top of a material, and that is just in early proving stages, so we don't have any data on that. Some of the improvements we're making on the prototype device that I brought with us are monitoring any drift in temperature. So the device itself will monitor any drift at 0.002 degrees Celsius a second, and a test will not begin if drift is any higher than that. So the needle is inserted and comes to equilibrium with the sample, and if the sample temperature is changing at a more rapid rate than the 0.002 degrees Celsius, then the device will not start testing for conductivity until that stabilizes. There is an option where the user can override that and begin the test if they need to, or if they wanted to. We're also applying the Blackwell solution to Fourier's equation, and so that takes into account the finite probe size and the contact resistance that can be an issue. One of the advantages to using this sort of device, the probes themselves being relatively small, is that you can create thermal dryout curves if that's a need. And so if you have the water, if you know the water content, you can, just by simply weighing and drying the sample, you can have the sensor itself inserted in the sample during the drying process. And the needles are designed to be heated. They're rated to 150 degrees Celsius, so you can insert those into an oven while you're drying the sample and create a dry-out curve of your sample. Here's a quick example of a dry-out curve done in some sand. So this point here, it was the as-found point of the sand in the field. It was collected, it was saturated, and then dried in the oven with the sensor inserted into the sample. And if you'd like more information, this is just a brief explanation of that. If you'd like more information on dry-out curves, just in general, I can provide that. So now on to some just kind of general information, things we found in the testing of PCMs that we've been doing. The information that's to follow is specifically on some gels and liquids that we've tested. I actually brought the gels with me for the workshop, so you'll be able to see those. So the transient line method is a good choice for phase change materials that are solid gels or liquids, but the liquids would need to be the same viscosity of water or less viscous than water. And the reason there is because, and we'll see in some of the graphs to follow, that induced convection can be a problem if you have a material that's more viscous than water. So the experiment with these materials, we had 4 samples total, 2 gels and 2 liquids. We had so we had gel and liquid version of both a 5-degree phase change material and a 15-degree phase change material. The gels retain their shape at warmer temperatures, and you'll see that in the workshop. So we took our probes and we inserted them into the gel and into the liquid. The liquid samples were put into vials with septa, with a lid with a septa, so we could insert the needle through the septa, and then we could stabilize the vial so that to reduce vibration. So once the needles were inserted, we placed the samples with the probes inside of this environmental chamber, and we cooled the chamber to -30 degrees Celsius. And And so the samples became frozen, and over about a 24-hour period, we warmed the samples up to about 50 degrees Celsius and measured with the KD2 Pro unit that manages the probes. We set that to continuous measurement mode, and so there's a data point, there's a measurement taken every 15 minutes. So here is the results from the 5-degree material. The liquid samples and the gel samples in both the 5-degree phase change samples start at the same temperature, and the phase change itself starts at the same point, which we expected, but the customer that sent in these samples wanted to confirm that, and that was the main point of them having us do testing for them. It's also, well, it's important to point out that the data here on the liquid samples is incorrect, and that is because once the liquid thawed and became viscous, the vibration from the environmental chamber created that induced convection. And so what we did is after the test or the environmental chamber was finished, we took the liquid samples out, let them come back to room temperature, and did the test outside of the environmental chamber, and results were down in this range, as the gels were. Here's the 17-degree material. Again, the vibrations in the liquid after it's thawed and comes back to its liquid state. And so same thing, we did the same thing. We took the samples and let them come back to room temperature and took their conductivity measurements again. It was interesting to note that this material the starting conductivities for the liquid and the gel are slightly different, where in the 5-degree material you can see that they're the same, and then they're different here. And though the phase change occurs at the same time, we're not really sure, and the customer didn't have an explanation for why those had different conductivities at the beginning or in the frozen state. It was also interesting to note that the 17-degree material here, the gel has a slightly higher conductivity than the 5-degree gel and liquid, but that the 17-degree liquid has a lower conductivity. So the 5-degree gel and liquid fall in between here, and they're starting conductivities in the frozen or in the solid state. So just in conclusion, we've done our best to create a device to measure thermal conductivity in a fast, reliable way that is as accurate as we can and as we are currently capable of making it, given the current technologies and the capabilities of our devices. And we continue to make improvements as technology advances, so that we can apply these solutions to Fourier's equation over time. And then it is just, although we haven't done a lot of testing, the data shows that you can use our thermal conductivity device to monitor or to confirm the phase change point in phase change materials. Are there any questions? Thank you very much.